All right, so we can calculate delta G, we can calculate delta S, we can calculate delta H. We want to think a little bit about what does delta G really tell us. And one way to think about that is by looking at the temperature. Now, we know if delta G is negative, that's a spontaneous reaction. So we can think about the sign of delta G in terms of the signs of the components, right? We know that temperature is always positive. Delta H, if delta H is negative, an exothermic reaction, that's going to tend towards reactions being spontaneous because negative delta H is likely to contribute to negative delta G. We're subtracting the entropy term, so if entropy is positive, that's going to tend towards reactions being spontaneous because we take the positive value of entropy, we multiply by the positive temperature, and then we're subtracting that from enthalpy. So if the enthalpy is negative, the entropy is positive, that reaction is going to be spontaneous no matter what the temperature because delta G will always be negative. Now, the opposite case, if the enthalpy is positive and the entropy is negative, that's a reaction that can never be spontaneous. It does not matter what the temperature is. That will always be a non-spontaneous reaction because delta G will always be positive. Now, where things can get interesting is when the enthalpy term and the entropy term are pointed in different directions. Say the enthalpy is negative, so the enthalpy is kind of pushing the reaction towards spontaneity, but the entropy is negative. The entropy is pushing the reaction towards non-spontaneity. So it's almost like the enthalpy is saying, yes, let's do this. The entropy is saying, whoa, hold on. Now it becomes an issue of which term is larger, the magnitude of the enthalpy term in our delta G equation or the magnitude of our entropy term in our delta G equation. And the entropy term is dependent on the temperature. So if delta H is positive and entropy is positive, or if they're both negative, then temperature is going to determine whether that reaction is spontaneous or not, because what the temperature is will determine the magnitude of the delta S term. That's kind of what we're looking at in this particular equation. We want to figure out the effective temperature. So we're looking at the decomposition of a certain compound, so it's nickel with 4 carbon monoxides attached, into nickel and carbon monoxide. We're told delta G is 40 kilojoules per mole at 25 degrees C. So at 25 degrees C, this is not a spontaneous reaction. It's not going to happen. But what we want to do is figure out at the temperature at which the reaction would become product favored or spontaneous. So we're trying to solve for a temperature here. So we're given some information here. So we're given enthalpies of formation and standard entropies. So we want to calculate the enthalpy change and the entropy change respectively for this reaction. Now we've seen that a few times, so that's the summation formula, sum of the products minus sum of the reactants. And again, I looked these up, put them in a table here so that we can do this problem a little more quickly, but often you'll need to look these up to do this type of problem. So products, nickel, that's its elemental form, so that's 0 for enthalpy. The other product is carbon monoxide. There's 4 moles, so 4 times negative 110.5 kilojoules per mole. That's our products. We want to subtract out all the enthalpies of formation of our reactants. And for the nickel tetracarbonyl, that is minus 632. And so combining all that together, we get positive 190 kilojoules per mole. Right, so enthalpy is positive. So enthalpy is saying, whoa, I don't want to do this reaction, right? It's breaking the bond between nickel and the carbon. Enthalpy doesn't like that. We don't want to break bonds. We need energy to break bonds. Entropy, though, on the other hand, the entropy change for this reaction, right? Sum of the products, so that'll be nickel, 29.87, plus 4 moles of carbon monoxide. That'll be 4 times 197.67. And then we're going to subtract out the contribution from the reactants. So 1 mole there, 320.1 for the reactant. So if we combine all of that together, that comes out to be 500.45 joules per k-mole. Now it's positive. That means entropy likes this. So entropy wants this reaction to happen. Enthalpy doesn't, right? And what the temperature is going to determine is which term wins out, whether that makes the reaction spontaneous or not, by making delta G have a negative value. Now we're going to combine enthalpy with entropy, so let's change this to kilojoules so that we can do the subtraction later on. So divide this by 1,000, and that would be 0.5 kilojoules per k-mole for the entropy change. Now, if we plug this in to our equation, we're going to use a delta G value of 0. So 0 is where the reaction is at equilibrium. 0 would be in between where the reaction goes from spontaneous to non-spontaneous. So plugging into this equation, if we plug in 0 for delta G, 190 kilojoules per mole for delta H, right? And we're solving for the temperature. So T is our variable here, our unknown, and our entropy term is just 0.5, right? So this gives us an equation we can solve for T. So if I rearrange a little here, I get 190 is equal to the temperature times 0.5, or the temperature is equal to 190 divided by 0.5, which is 380. So we would need to run the temperature up to 380 Kelvin to get this reaction to switch from being non-spontaneous, like we see at room temperature, to becoming spontaneous. And then at any higher temperature, the reaction would stay spontaneous. So at higher temperatures, we're taking advantage of the entropy of the reaction to cause it to be spontaneous, even at the cost of the enthalpy of the reaction. Okay, one last example here where we can compare the free energy to an equilibrium constant. So we're given KSP for silver chloride is 1.8 times 10 to the minus 10th. We want to calculate delta G for precipitation of AgCl. So the first thing we need to recognize there is that KSP, we know that SP stands for solubility product. This is for solubility. That would be the forward reaction where AgCl dissolves into silver and chlorine. What the question's actually asking is precipitation. That would be the reverse of that reaction. So the reaction we're interested in, the reverse, instead of being concentration of silver times concentration of chlorine, it would be 1 over the concentration of silver and chlorine. So the equilibrium constant for precipitation would be 1 over the solubility product constant. So if we take that value, 1.8 times 10 to the minus 10th, and invert it, that's a button, I don't use that often on my calculator, but there it is. That becomes 5.56 times 10 to the 9th power. So that's our equilibrium constant. That's what we want to relate to delta G. But once we have the correct equilibrium constant, we really just have to plug in. Delta G is equal to minus RT times the natural log of this equilibrium constant. So negative sign. Now R here, we're used to using R in units that are convenient for gas laws. There is another version of R in terms of joules. So 8.31 joules per k-mole is the appropriate value for this type of problem. That'll give us our energy in joules. Since delta G is usually kilojoules, we can change that at the end. This is at 298 Kelvin. And then the last term will be the natural log of the equilibrium constant, 10 to the 9th. Okay. So if we plug that in, multiply by the other values here, we end up with negative 55,567 joules per mole. And to get that into the right units for delta G, we just divide by 1,000 to change that to kilojoules. So that would be minus 55.6 kilojoules per mole. That's the free energy for that reaction. So that tells us that, yes, precipitation is spontaneous for silver chloride. And that will wrap up chapter 17.